In the first part of this chapter, we learned how to construct a rate law given some experimental data, and then how to use that rate law. Remember, a generic rate law for two reactants would look something like this. But you'll notice that in this rate law, we don't know anything about the actual time. And so what we want to do now is look at the relationship between concentration and time in these rate laws. This is going to be very helpful because it can give us information, for example, how long does it take for a reaction to proceed, going from reactants to products, or how long does it take to get a certain concentration of reactants or a certain concentration of products. Those are very important things to know, especially in industry when you are studying chemical reactions and trying to come up with ways to manage them, affect them, and use them in order to be more economical. Now, we also mentioned that there were three kinds of reactions: first-order reactions, second-order reactions, and rarely a zero-order reaction. Remember, first, second, and zero tell us whether or not a particular reactant affects the reaction rate linearly or exponentially or not at all. So when we begin with this observation right here, that says that the change in the molarity of reactants divided by the change in time equals some proportionality constant K times your concentration. Remember here, R stands for reactants. R does not stand for rate. And the idea is like this. If I have a high concentration of cars on the highway, the change in the number of cars divided by the change in time, where we're looking at how many cars are going to be in car accidents, diminishing my concentration of cars, this is going to be proportional. The more cars I have on the road, the more of them are going to be removed from the road every interval of time as they enter into collisions or run out of gas or exit the highway, whatever the case may be. So that's what that equation means. Now, using the methods of calculus, integral calculus, and someday you're going to learn it looks something like this symbol when you integrate. We're actually going to do one in our nuclear unit, show a first order reaction and take the integral of both sides. But until then, if we use integral calculus, we end up with this equation right here. Notice we've brought the negative sign over to the right. And that tells us then that this ratio of particles or molecules or whatever it is, the concentration of those particles of my reactants at some time t compared to the concentration I started with, that's what the little 0 or O means, molarity of R sub aught means my initial amount, is always getting smaller and smaller. And so we need a negative sign because we're going to expect our graph to have a negative slope. Sometimes we even don't really care about the concentration at time t or the concentration that I started with. All we care about is the fraction, which we can convert into a percentage change. And this is a first order rate law, but rate laws in general, you see, have these advantages that are in the bullet points. we can calculate the fraction after some amount of time. And once we know that, we can calculate K. K then will be good for this particular kind of chemical reaction with other molarities and concentrations and so forth. Or if we know one of these, we can calculate what the other would be if we know the time interval and the value of K. So there are a lot of advantages to having these integrated rate laws. Notice that for a K, a first order reaction, it's independent of your concentration. We're looking at the change in the concentration from some beginning point, the little letter O or 0, to some final point at time t. That means that in this fraction, it doesn't matter what R is. It could be molarity. It could just be moles. It could be grams. It could be number of atoms, number of molecules. It could be gas pressure. It doesn't matter because their units are going to cancel out in the fraction. And here's a problem where we are given the initial concentration right there, and we're trying to find our final concentration right there. We know the value of K in this problem, and we're trying to find the amount of time. So it just becomes an algebra problem. Or if we look at this, which is going to be something that'll look familiar in lab 12, having to do with the decomposition of hydrogen peroxide. In this problem, we know the value of K, and we're trying to solve for the fraction. We're not interested in either the final or the initial concentration, just what is this fraction after 100 minutes. Now, by the way, you'll notice that you're always given the temperature. That's because your value of K could be different at different temperatures. So it's just common practice to specify the temperature even though the temperature is not in the equation. That is because there's a correlation between the temperature and the value of K. Also notice that we're talking about 100 minutes here. So we want to make sure whatever units we end up with are also in minutes. So here we're just taking the natural log of this whole fraction right here. You could just as well just call it x. The natural log of x equals a negative 0.106. And that number, of course, came from multiplying K times the time, and don't forget that negative sign. So we get a fraction of 0.9, which means that after 100 minutes, I still have 90% of my initial concentration, and 10% of it has decomposed. Now, the second order reactions uses a different equation, and again, it's the result of integral calculus. And again, we notice the relationship here that my rate of change, the change in molarity, the change in the concentration of R over time, again, depends upon the concentration of particles that I start with, but it's second order. That's where that 2 comes from. Second order, there's that exponent of 2. And you take the integral calculus, use integral calculus in both of those, and you get this rate law here. Again, you don't have to memorize this. This would be given to you on my test as well as on the AP test. You should just know that this is the one for a second order reaction and not confuse it with the one for a first order reaction. And once again, we simply have to look at the data. We're given the value of K. Notice they specify the temperature, pretty high temperature for this reaction to take place. It does take place naturally, which would be way down at 20 degrees Celsius, but you'd have a different value of K for that. If you look at this value, to undergo a change of 30 liters per mole per minute, that is a very, very rapid decomposition. And that would take place, obviously, at a higher temperature. And again, we are given our initial concentration and the concentration after time t. So we plug our numbers in, and we see that this is going to take 3.3 minutes. Now, zero order reactions, I remember a question being asked about this. These are very unusual. And typically a zero order reaction, which means that the reaction does not depend upon the molarity of your reactant, you're initially tempted to think, well, then how can there be any rate if it doesn't depend upon the molarity of my reactant? Well, these are kind of constrained reactions or jerry-rigged reactions. In other words, maybe we are continuously adding reactants as the reactants are being used up. Maybe there are other reactants that are affecting this rate. Sometimes it's hard for some of these reactants maybe to react because they might be all stuck together into a big clump or adhering to the sides of the beaker. So it's rather unusual circumstances that you would have a zero order reaction. In any case, you can see that in this reaction that your change in the molarity of R equals KT, and it's starting to look like Y equals mx plus B. Y equals mx, where B, in this case, would be 0. And in fact, all three of these reactions can be expressed in terms of Y equals mx plus B. In order to force fit a linear line, sometimes you have to take natural logs, sometimes you have to take reciprocals when you go to graph it in order to force fit a straight line. Notice also that the zero order is negative and this is negative, but because we have reciprocals for second order, we have the positive. Now, unfortunately on these pages, when they refer to something like figure 15.6, they're not on the same page. It's way over on this other page, which we can go to for a minute. Again, you can see the negative slope. It's also nice and linear. Notice we're graphing the natural log of pressure. And because we're talking about concentration, gases could sometimes, in fact, usually it's easier to measure the concentration of a gas with its pressure rather than in molarity, because we have gas pressure sensors as probes for our lab quests, for example. But again, in the fraction, the units are going to cancel out. So we can just leave our pressure readings as atmospheres or millimeters of mercury or kilopascals and leave it in those dimensions. We don't have to convert it into anything because they are going to cancel out. Figure 15.8 is on another page farther on down, but here's figure 15.7. And here we have our reciprocals right here. This is a second order reaction. Remember, that's the one that has the reciprocals. Here again is a summary of our rate equations, the results of using integral calculus, the fact that we're going to have a straight line plot when we graph these things, whether our slope will be positive or negative. And again, we get these kind of weird units for K, which are different depending upon whether it's 0, first order, or second order. Oftentimes, we don't generally care about the units of k other than to note whether or not the time is in minutes, seconds, hours, or whatever. Now, this is an extremely famous equation right here. This can be used in economics when you're talking about regular withdrawals of money percentage-wise from a bank account. This could be used in biology, for example, when you're talking about a regular percentage of organisms in a population in a field somewhere, either being eaten or leaving or migrating or dying or whatever. Very, very, very common statistical equation. We're going to see it again when we talk about how many radioactive particles are left as a radioactive material is undergoing radioactive decay. And we're actually going to derive that equation then. Suffice it to say that the natural log of 2 is 0.693, if you're wondering where that weird number came from. In any case, you see that my half-life is inversely proportional to my decay constant. And what do we mean by half-life? Well, a half-life is how much time it takes for half of your particles to be remaining. Let's imagine, for example, that I had a big shoebox. Try to quickly draw a shoebox here. And in that shoebox, I put, say, 1,000 pennies. And I shook up the box. And the amount of time that I take to shake up the box, we could say, we're going to call that a T 1/2. Because after I shake up the box, if I take all the pennies that came up heads and take them out of the box, I will have approximately 500 pennies left. So this would be the amount of time it took to end up with half of the number of pennies that I started with. And then I shake up the pennies again, remove all the heads, which will be about 250, and now I'm down to about 250 pennies left, give or take. And then I can shake it up again, which would be another half-life. And now I'm down to about 125 pennies, give or take. And you can anticipate then that your graph is going to look something like this. There's your starting, and if this is T, if this is your initial amount, we could say your initial concentration of reactants, I'll call that 0. Right here would be your concentration of reactants after some time T, and this time right there is called a half-life. And then I'm going to have another half-life. And I'm going to have another half-life until statistically I don't have enough pennies to accurately continue to draw the graph. So when we go ahead and graph this molarity in terms of moles per liter, this is a 0 order reaction, which is why, unfortunately, it comes right after the reaction that I was just talking about. This is a 0 order reaction, which would automatically be linear. And here's the one where I was drawing the half-life. So if I started with a gas at 8 millimeters of mercury of pressure, and then at some point I have half that pressure, and some point I have half the half, and some point half the half of the half. And so you can see that as you make this graph, This is your first half-life right here, is your first half-life. And then over here, here's going to be your second half-life, and over here would be your third half-life. And of course, if you undergo three half-lives, and you take 1/2 times 1/2 times 1/2, or another way of saying it, half of a half of a half, you get 1/8, which means after three half-lives, you're down to 12.5% of what you started with. Or you could say that 87.5% of your original reactants have now turned into products. And here's an actual example using a radioactive isotope of radon. And here they're using atoms as a measure of concentration, because you're in a flask, a closed flask. And so if you have this many atoms to start with, so that would be at my starting point right here. How many atoms will remain after 1 month, which is 30 days? Well, what you need to do here is to find out, well, just how many half-lives is 30 days. And if it doesn't come out to be a nice even number, because you could do it in your head, you would have to resort to using the half-life equation right here. And here's your decay constant K. Notice the negative sign because it's diminishing. 30 days. And we started with atoms, so we're going to end with atoms. And so you can see we went from 10 to the 13th down to about 10 to the 11th. We reduced it by, let's say, a factor of about 200. Because we went from 4 down to 2, and 10 to the 13th down to 10 to the 11th. We will continue on with section 15.5 in the next screencast.